Swayam Prabha. Digital India. Educated India.
Hello everyone. Now our present topic is response of the card to a step change in feed. In our last session, what we have discussed, the load at different section in the carding machine, in the particularly in cylinder, doffer and Likharin zone also. Now, here our main focus will be that how the load on the carding machine increases when we start the production, because it is initially it is empty. We start the production, that is we start feeding the fiber bat at the back, and after reaching the steady state, again if we add some more material, suppose we want to increase the productivity by increasing the linear density of feed material, during that time how the card will respond, and also when we again drop the feed, during that time also how the card will respond, that we will discuss. Okay. So, here first what we will do, response of the card due to sudden and sustained rise in feed. So, when we suddenly increase the feed or sustained feed, so that how the card will respond, that we will discuss here. So, response due to step change in feed, here in this part we are discussing the step increase in the feed, and also that step rise, step drop. So, here if you see, suppose this is the output. So, input in the card is basically equal to the productivity, production, P is the production, considering the eliminating the effect of the waste percent. So, production, so input material is P, which will be consistent, the P unit per say time. So, it will, that feed material will continue up to time T1, and then after T1, at time T1 we start, we suddenly increase the input material to delta P, increase, and that will continue. So, P plus delta P. So, this is actually P plus delta P, that will continue up to time T3. Okay. So, and at T3 we suddenly drop the feed by again delta P, and the feed input rate will be P only here. Now, during this time how the card respond, that we are going to discuss here. Now, if you see the diagram above it, so output material, if we see here the load on card, so output will be, so increases. So, this is input. So, output will not immediately increase, because the card will get loaded, card components like mainly cylinder will start getting loaded. So, that loading will continue up to certain time. So, this shaded portion, hashed portion by green color, this shows the card is getting loaded, and this loading time is, it will continue up to T0. T0 up to T0 the loading will continue, and at point A the saturation will reach, and that is continuing up to T1. So, that up to T1 this total load on card becomes C1. So, initially the load on card was 0, then gradually load on carding machine increases, and it is actually stabilized at C1 point. Then again when we suddenly increase the feed input material by delta P, the load will again increase by this up to say C point. Okay. So, that is actually it is a C2 is the total load, but that will not increase again by step suddenly. We are changing the feed suddenly, step change in feed, but the card will take time, it will get gradually loaded, and which is additional portion loaded is given here. So, total load. So, this is this plot, the red color, it shows the level how the loading takes place. It is not straight line, it is some exponential curve. So, that it follows certain curve it follows. So, here the total load after certain time, say T3 at T2 the total saturation or stabilization reached at T2. So, that means T0, so T0 up to T0, that means here 0 to T0 time, that initial loading is there, card is getting loaded, and it continues up to T1 saturation level or sorry stabilization level, and at that T1 we increase the feed once again, and which results again gradual increase in load, and it reached C2. So, initial stabilization time load was C1, and after certain time it becomes C2 stabilization load, and it reached at T2 time. So, at T3 what we have done, we have again reduced the feed input material by delta P, sudden input, but the card load will not change suddenly, it will take time gradually, because fiber will get transferred from cylinder to doffer at with a time certain rotation will require. That is why it will again drop, and it will be stabilized at C1 again at time T4. That is the situation here, and we will now try to analyze how this the card is responding. Let the amount of fiber fed to the cylinder per rotation is P. So, that means input material per rotation we are feeding to the cylinder is P. Okay. And step increase at time T1 is by delta P, okay, at time T1 delta P. Now, at time T2 there will be step decrease by delta P. Okay. At time T1 delta P. Now, at time T2 there will be step decrease by delta P. Okay. At time T2 there will be step decrease by delta P. Okay. At time T2 there will be step decrease by delta P. Okay. At time T2 there will be step decrease by delta P. Okay. At time T2 there will be step decrease by delta P. Okay. So, before reaching the steady state condition, what happens? So, before reaching the steady state condition, when we start feeding, so that cylinder will get, the total card machine will get loaded with the fiber. So, output of the cart will not increase immediately to level P. So, it will take time. So, as I have mentioned, till T 0 the output actually gradually increasing. So, C is increasing, this curve is C, okay, before it reached to P. So, at point P after time T 1, so T 0, the C will become P. So, that will be again then constant. Okay. Now, at this point zone, the load is gradually increasing. Okay. C is the given by card, it is a card load. Okay. After reaching the steady state condition at T 0, at time T 0, what happens? The output of the cart till time T 1 it becomes constant. So, output of the cart become constant, that is C 1, which is equal to P, and that is constant. Okay. Now, transient period for the feed P, that is the transient period here. So, what is the transient period? 0 to T 1, that is this period, T 0 is the, at that period there is a transient period. Okay. And so, now we will discuss. So, this is the transient period T 0. Now, let us discuss when the feed is suddenly rise by delta P. So, at time T 1 the feed is suddenly rise by delta P before reaching the steady state stage at say at T 2. So, what happens? The output is gradually increasing. So, output gradually increases. So, that is with the time till T 2, and here the output is again increasing, it is not constant. So, after reaching the steady state condition at T 2, what happened? The output of the card with time, okay, until time T 3 it becomes constant. So, what is that? This is C 2, okay. C 2, C 2 is nothing but C 1 plus delta P. So, which is constant here. So, this is constant here, and in this zone this is the transient zone, okay. And transient period is actually by feed P plus delta P. So, when we are feeding P plus delta P, the transient period is T 1, okay. T 1 is the transient period. So, during that time T 1 time the output gradually increases, okay, and output is gradually increasing. So, this because of the loading, additional loading on the cart. Now, when the feed suddenly increases here, what happens? During the transient period T 1, so mass of the fiber fed to the card will be total mass. So, this is per revolution, okay, C 1 plus delta P is the mass of the fed, total mass Q1 fed to the card will multiplied by the time. So, these are the per unit time multiplied time. What is the time? Say T2 minus T1. During this time mass of the material fed. So, C1 plus delta P is the fed per unit time, and if we multiply by this time, it will be total mass fed to the card. Here is the total mass. So, you can see if we, this total area of this rectangle is the total mass of the card fed, mass of the material fed to the card. Okay. Now, so this total mass is fed, but it is not actually being delivered. So, that delivery, the output is not the complete output. So, this part, this shaded part is the portion where additional loading in the card, which remains in the card. Okay. That means, mass of the fiber delivered from the card, okay, is this one. So, T2, so delivered from the card. So, T2 minus T1. So, if this is the function of this card, okay. So, this is the function of this curve T1 and T2 during the time T1 T2, and Ft is the function represents the dependence of the C on the time during the transient period BC. So, this is the function is represented by Ft. This function actually can be derived, and it depends on many factors, depends on the type of fiber, diameter of fiber, length of the fiber, wear point density, construction of wear point, height of wear point. So, there are many factors, okay, and speed of machine. So, that is that function, it is unknown function, but this function can always be derived for a particular set of condition. Even type of fiber, for polyester this function will be different, for cotton it will be different. Okay. So, that can be derived. Now, so we will stick to this zone, okay, suddenly rise. So, total hatched area, what is the hatched area? Q1 minus Q2. So, this hatched area BCG, okay, the amount of fibers retained by the cylinder in addition to OPA. So, this total fibers will be retained by the cylinder, okay, cylinder surface, because cylinder is the only portion where fiber is retained. Otherwise, a doffer always releases fiber, and Licarin also releases fiber. So, card loading is effectively the load on the cylinder. So, this is the total fiber is retained by the cylinder. Now, here we can see. So, next step is that when the sudden fall in the feed. So, at time T3, suddenly the input material is dropped by delta P. So, when input material is dropped before reaching the steady state condition again, it will not suddenly reach the steady state condition. There will still be some additional load on the cylinder, which is shown by the hatched line. So, output of the card till time T4 will be decreasing, that we have discussed earlier, and after reaching the steady state condition, the output again becomes C1, which is there, which was there between T1 T0 to T1. Okay. So, beyond T4 the output will again be C1. So, the output of the card till time T4, okay, after the time T4 is equal to C1 equal to P, which is constant again. So, the transient period of the feed is P plus delta P. For the feed delta P is T2. So, this is the transient period. That means, here now this will be actually transient period, it will be P plus delta P was there. So, we stopped that. We stopped feeding. So, when the feed suddenly falls by delta P, so in this zone, so this will again follow some function. So, during this transient period T2, the mass of the card, okay, mass of fiber fed to the card is Q3. So, that is what is Q3? It is C2 minus QP. So, this is C2. So, minus delta P, C2 minus delta P multiplied by T4 minus T3. So, that is the total mass fed to the card during that time, the Q3. So, here mass fed is Q3, okay, and that is we can get here, we are feeding mass here. So, earlier mass feed was this one, okay. Now, we are feeding the mass because we have suddenly stopped. So, this is the mass fed, but here you can see the cylinder is still loaded. Okay. So, mass of fiber delivered from the card, what is that? So, F t dash is the, this is the function F t dash of this curve F t dash. So, T3 to T4 F t dash dt. So, with that function we can get. So, this is the total curve we will be getting here. Now, F t dash is the function representing the curve d e. So, when feed is suddenly it suddenly falls by Q p, what happened? So, Q 4 minus Q 3, okay, Q 4 minus Q 3 the hatched portion. So, by doing this, so what is that? Let me show it again. So, Q 4 we are getting, what is Q 4? So, Q 4 is the portion, this is the Q 3, Q 3 is, this is the Q 3, okay, and Q 4 we are getting, this is total, entire portion is Q 4. So, area under this curve, area under this curve is Q 4. Okay. So, that means Q 4 minus Q 3 is the additional load. So, excess material delivered than the feed material. The beauty is that when suddenly we reduce the feed to P, but card is still delivering the higher quantity than P. So, what is the feed? That means the additional material was there in the on the cylinder. So, that is feeding and it will go till T4. So, now we will discuss the next step here. During the carding, mixing also takes place. Why? Because in the card we will see the particularly in the cylinder the mixing takes place. That is a main zone where mixing is taking place. Now, how is it taking place? Let us discuss. Suppose this is cylinder, here is Licarin, and Doffer. Now, suppose we are feeding material. Okay. Now, this is one material, another is fed here. So, red color fiber and green fiber. So, two fibers in the from it is coming from blow room, they have not been mixed properly. Now, what will happen here? The Licarin will not be able to mix because this fiber will go at the this red fiber will go at the front portion, it is going. Now, it is coming to the cylinder. Now, cylinder it is coming, cylinder is giving few portion, that is transferring few portion to draw frame, but the red fibers are actually it is loaded on the cylinder in the form of one layer, few layers. Now, again by that time the green fiber comes and green fibers will also form layer. So, this mixed fiber will come to the Doffer. So, it actually it mixes by in the layer form, okay, in the carding machine. So, that is the process. We will now try to analyze these things. So, this is the carding machine. So, here Licarin, cylinder, Doffer. Now, mixing of fibers in a card takes place on the cylinder. So, mainly cylinder is responsible because Doffer and Licarin they cannot mix, because Licarin takes material from feed roller and directly it transfers the material, and similarly in Doffer it directly transferred take the material and transfer to the delivery zone. Doffer, depending on its collection power, takes only part of the fibers presented. So, it is taking the fibers whatever collection fiber part is there. So, suppose there is a 100 gram fiber here, it is giving to the Doffer, but Doffer cannot take the 100 gram per say per revolution, per minute, per second say. Okay. Here Doffer will take part of this, say 10 gram, rest 90 gram will be there with the cylinder. So, that will actually rotate as I have mentioned. So, that will mix with the subsequent fibers layer. So, rest goes back to the return fiber layer and joins the freshly laid fibers from the Licarin and approaches Doffer again. So, it is going back, okay, remaining fiber, and then it is mixed with the fresh fiber, and these two fiber, fresh fiber and earlier fiber are mixed and again approaching to Doffer, and this process continues. So, Doffer now removes the a part of the combined freshly fed and returned fiber layer from the previous cycle. So, that actually helps the mixing. The rest of both layers go back. So, mix, and again it takes portion of that fiber, again this mixed fiber goes returned back, and again it rejoin the freshly layered freshly fed fiber in the third cycle. So, in this way, so there will be a n number of cycles, it keeps on actually mixing. This process repeats, thus the fibers fed during the several successive cylinder revolution get mixed up. So, as already stated, the material on the card basis, particularly cylinder, are presented to the doffer. So, this is the term BN, consisting of fiber fed at different points of time at various portion of the feed point, like in the fiber feed bat at various portion, which can be represented by the following equation. So, let us see, this is the different equation that we have already discussed in last session, where we are discussing the loading, cylinder loading. So, B n is the fiber, actually cylinder, which amount of material which is presented to the doffer, that is there, where P is the production rate and gamma feed rate, and gamma is the transfer transfer efficiency. So, degree of mixing depends on the doffer transfer efficiency. So, gamma is the doffer transfer efficiency. The lesser the transfer efficiency, more material will be given back to the cylinder and better is mixing. Now, let us consider one situation where, suppose here the doffer's transfer efficiency is say 100%, what would happen? So, fiber, whatever fibers are coming, the cylinder to liquor in transfer efficiency is 100%, 100% is taking, and the fiber, it is actually here the fibers are getting carded and doffer is taking 100% of that. So, that what does it mean? This portion at the bottom portion, it will always be clean, empty. So, that means the what we have discussed earlier, so there is no chance of fiber mixing. Okay. So, that will be the issue. So, we need, so the question is that, is it right, or is it better to have 100% efficiency? The answer is no, because 100% efficiency we will have two issues. One is the blending will not be there or mixing will not be there, and second is that the proper opening may not be there during one actually carding zone. During the carding zone, fibers may not get opened properly. So, it may have naps. Okay. It may, so for proper opening, if we do repeated carding, then the fibers get segregated properly. So, lesser the transfer efficiency, more material will feed back to the cylinder and better mixing will take place. So, we try to keep lesser transfer efficiency, but at the same time very low transfer efficiency, what will happen? Very low transfer efficiency means we have feeding is going on and doffer is taking less quantity of material, which will actually result the increase in cylinder loading. That is also not correct. Higher cylinder loading means the thicker layer between the, this is cylinder, this is flat. If the higher cylinder loading is there, there will be thicker layer of fiber around the cylinder, and that will affect the carding performance. So, too low transfer efficiency is also detrimental to good carding because increase the cylinder load. So, we have to optimize the transfer efficiency, and transfer efficiency, as we have discussed, the transfer efficiency depends on the various factors, the like cylinder wear point density, type of wear point. So, we have to have optimized transfer efficiency. A balance is therefore needed. So, mixing of fibers is that now we can see here. So, different layers are there. So, this is suppose different fiber layers are there. This is actually previous layers, and this is material belong to the present cycle, last cycle, the loading is there, and these total fibers are the total layers are actually transferred to the duffer. So, that these are getting mixed and it is transferred to the duffer. Now, we will discuss the theoretical investigations. So, into transfer efficiency. Transfer efficiency, as we have discussed, it is very important as far as the quality is concerned, cylinder loading is concerned, and also the better mixing. So, let us now try to discuss the theoretical investigation into transfer efficiency. So, Baturin's actually that he has analyzed, he has given some theory. So, the theory is that it's as per as his analysis, it is basically the magnitude of loading of cylinder clothing depends on the proportion of fiber transfer to the duffer. So, that is that if the fiber transfer proportion is less to the duffer, then loading on the cylinder will be more, which in turn depends on the entrapment power of both cylinder and duffer clothing. So, how much fibers are getting entrapped. So, if the duffer clothing entrapment power is more than the cylinder, then the cylinder loading will be less. But if it is entrapment power is, if it is less, the transfer efficiency will be less and cylinder loading will increase. The entrapment power depends on the different factors. So, what are the factors? What are the parameters? One is the density of wear points and their inclination, that is very important. So, wear point density and their inclination. Wear point density is very straightforward, because if the density is more, that means it will try to attract more fiber, but inclination will try to analyze mathematically. Then diameter of roller. So, what is the diameter of cylinder and duffer, the ratio, that in that way it will result the transfer efficiency, and the rotational speed of the cylinder or duffer. So, that these are the parameters on which the transfer efficiency depends. When the entrapment power of both cylinder and duffer is assumed to be the same, the load on both will become the same. So, entrapment power, what do we need? So, depending on that we have to adjust. So, we know the parameters, we can actually decide the what will be the wear point angle, wear point density. So, this we can do, we can actually measure the, we can control the the entrapment power. So, QC equal to QD, that means load on cylinder and load on doffer will be same if the entrapment power is same, where QC is the cylinder load on cylinder clothing per meter, per unit length. What is the cylinder load, and QD is the load on cylinder on doffer per meter, gram per meter. Okay. It is nothing but the linear density of the web cylinder load. Now, influence of teeth density, that we have already discussed. These are the parameters. Now, we will discuss each parameter one by one. Okay. So, influence of teeth density. So, what is the effect of teeth density? In actual practice, the wear point of cylinder and doffer differs. So, we try to keep the wear point density of cylinder and doffer different, thus the entrapment power will vary in proportion of their wear point density. So, that is how. So, I have already mentioned, higher the wear point density, that means more surface of pins are presented. So, more entrapment power will be there. Then see QD, doffer load, entrapment power of doffer divided by entrapment power of cylinder is actually proportionate. So, NCD by NCC, that means number of wear points per unit area of doffer divided by wear point density by of cylinder, which is constant for a particular machine. This is constant, this is expressed as K1. So, it is a wear point tooth count or wear point density, number of tooth per square centimeter. So, it is typically around 110 to 180. So, 150, 160, that is a typical value, but differ depending on the manufacturer or depending on the type of fiber, it may vary. And on doffer, it is a wear point density is typically 50 to 80. That means, entrapment power of cylinder is higher than the doffer. Okay. So, K1 is always less than 1. If the doffer entrapment power is more, then transfer efficiency will be high. So, in that case proper carding may not take place. So, QD equal to K QC from that equation, and K1 is the coefficient characterizing the ratio of entrapment powers of card clothing in relation to the wear point density. So, K1 is the actually the entrapment power ratio with respect to only the wear point density. So, if we talk about the only wear point density, then we calculate K1. Okay. K1 constant is basically related with the only the wear point densities. Now, next parameter is the inclination of wear point. You will see in carding, the cylinder and doffer wear point inclination are different to actually affect the to influence the transfer efficiency or holding power. Now, this is the diagram which shows the wear point inclination. So, here beta 1 is the wear point inclination of the cylinder and beta 2 the wear point inclination of doffer. Okay. Now, the red color of fiber is being gripped, actually is under the action of both cylinder and doffer. Okay. So, here you will see that point to point that action is there. So, between the cylinder and doffer they are in the opposite direction. Okay. Now, here it is a point against point. So, here the red color are it is a fiber and there it is in connection with the both cylinder and doffer. Now, the fiber is being loaded, it is a force applied on fiber is R. Now, this R force is actually we can this load on fiber we can have two components. If we see the wear angle you can see B1 beta 1 for cylinder is 40 to 60 wear point and the wear angle of doffer beta 2 is 35 around 35. So, wear point angle in cylinder is little bit kept higher. Okay. Even for synthetic fiber it is further higher, this is for typically for cotton. So, why? Because that we need the fiber to get transferred to the cylinder doffer. Okay. That is a basic idea, fiber should get transferred. So, if the cylinder wear point angle is low, then the cylinder that where fiber will have difficulty to get transferred from the cylinder to doffer. Now, we will see mathematically here. Now, beside density, inclination of wear point and diameter also influence the entrapment power, diameter of the cylinder and doffer. Now, here the force if we try to see this R force it has got two components R cos beta 1 and R sin beta 1. So, this is beta. So, again so this angle will also be beta. So, R cos beta 1 and R sin beta 1. So, beta 1 and beta 2 are inclination angle of respective wear points and mu is the coefficient of friction between fiber and the tooth surface, and for our for simplicity we can assume the mu for both doffer and cylinder we can assume same, because typically they are treated the fiber type of the metal we use are almost same. So, interaction between cylinder and doffer wear you can see the force with which each teeth acts on the fiber up to sets of reaction are. So, one against one tooth of cylinder is acting against the another tooth of the doffer, and in between one fiber is that the tension on the fiber is R. R can be resolved. It has got the following components on cylinder tooth C, this is a one cylinder tooth, the forces acting along the wear point. So, this force is acting along the wear point R cos beta 1, okay, and what it tends to embed the fiber with the carding clothing. So, this force as it is along the wear point, okay, so it tends to hold the fiber, it tends to grip the fiber along the wear point. Okay. It does not allow the fiber to be transferred to the doffer, and the force acting perpendicular to the wear point. So, this in this direction, that is r sin beta 1. So, these are the two forces, and that means which it gives the frictional force. So, what is the frictional force? R sin beta 1 mu. So, mu r sin beta 1, which resists the fiber embedment in the cylinder clothing C and its transition to the doffer. So, that is it resists the, because here is the force against the fiber is there. So, that force is acting here. So, that also resist. And it is transferred to. So, this is the force here. Now, on the doffer, this is the on the doffer tooth D, the corresponding component r cos beta 2. So, this is r cos beta 2 and r sin beta 2, this is r sin beta 2. So, these are the corresponding components here. Again r cos beta 2 will actually try to resist this movement fiber, it will try to pull the fiber, it will try to pull the fiber towards the doffer. So, influence of inclination of wear point here. So, we will continue with this. So, now there could be two possibilities, either fiber can be gripped by the cylinder, it is not transferring to the doffer, it goes with the cylinder, or fiber is being pulled by the this wear point D of doffer wear point, and it is going to the sliver or wave formation. These two possibilities are there. Event 1, the fiber remains on cylinder and gets carded by doffer. So, what doffer will do? Doffer will do only carding, fiber will remain on the cylinder, and doffer, because of the this wear point direction, the doffer will simply card the material, but it will not take the fiber to its surface. So, what is there? So, in that case, so r cos beta 1 and mu sin beta 1. So, if these two forces actually tries to restrict the fiber movement, and these two forces trying to actually restrict take the fiber away. So, if the possibility is there fiber remains on the cylinder, that means this force will be, total force will be more than the force on the doffer. So, r cos beta 1 r cos beta 1 multiply plus mu r sin beta 1 equal to more than r cos beta 2 plus mu r sin beta 2. So, if it is equal, what will happen? If it is equal, then the fiber will have the equal opportunity, either it can be transferred or it can be actually retained. So, but other factor, due to other factors fiber may get transferred. So, that way, so we try to maintain the wear point angle. So, in this case we can do, and for event 2, fiber passes on the cylinder doffer and it gets carded by the cylinder. So, fiber is getting transferred to the doffer and gets carded by the cylinder. So, in that case what is the condition here? Now, r just its opposite, r cos beta 1 plus mu r sin beta 1 is less than r cos beta 2 plus mu r sin beta 2, that is the condition. So, where mu is this. So, mu we can calculate, and so that is the basically condition which is required. So, frictional coefficient is related with the angle of wear points of the both of cylinder and doffer. So, that condition in that condition we can control the fiber transfer. So, generally event 2 takes place, okay, and fiber transfer continues until the equilibrium established as a result of reaction S2, okay, on the part of the fiber already passed to the doffer D. Okay. Now, this is the equation 2. So, that event 2 here, because we need fiber to get transferred. Okay. So, this is the condition here, and if we see this r cos beta plus r sin beta, okay, and minus S. So, with the S, what is S here? S is the result reaction, okay, minus S sin beta plus mu S1 sin beta 1. So, here you can see S1 and S2 are the reaction of fiber layer on C, this is the reaction of fiber layer on C, and S2 is the reaction of fiber layer on doffer. Okay. So, this again S1 and S2 if we can, so fiber layer reaction here S1, and that is if we again resolve S1 and S2. So, S1 has got two components. So, S1 sin beta 1 and S1 cos beta 1. Now, if you see here this r cos beta 1 and r sin beta 1, that is mu r sin beta 1, that they are actually trying to hold the fiber. Now, here this one, this is working against that, this one is working against the other direction, that is why it is a in negative sign is there, it is reducing that, whereas this r cos S1 cos beta 1 is actually increasing the frictional force again. So, that will be, so mu S1 cos beta 1. Similarly, for the doffer. So, this in this event 2, if we take into account the resultant reactions, okay, resultant reaction. So, that we can modify the equation, earlier equation 3. So, this will be actually valid where this will be equal in for both doffer and cylinder. So, influence of inclination it is continuing. So, till the steady state condition it is reached, the reaction S2 of the deposited fiber layer keeps increasing. So, this S2 will keep increasing, okay, till the steady state condition, and reaction S1 is decreasing with the transfer of the fiber from C1 to C2, C to D, cylinder to doffer. That means, initially the reaction force was high on the cylinder because of the fiber load, okay, more fiber load, but during the transition So, till the steady state condition is, the S1 is actually increasing and S2 decreasing. In steady state condition, each terms expressed in the equation 5 earlier, it should be 0. That is, in the steady state condition, this should be 0, okay, because these are actually should be balanced here in steady state condition, and this portion, this load on this should be balanced. So, in steady state condition, they should balanced, because fiber is getting transferred by based on the earlier equation. So, that will, otherwise that fiber transfer will get changed and it will actually affect the fiber linear density of the sliver. So, it cannot be sometime it is increasing and other time it is decreasing, it cannot be there. So, in steady state condition this should be, totally balance. So, hence you can see the S1 is R multiplied by cos beta 1 plus mu sin beta 1 divided by sin beta 1 minus mu cos beta 1. So, S1 is actually, we can calculate S1 based on the wear point angle and coefficient of friction and the force on fiber. Similarly, S2 is R cos beta 2 plus mu sin beta 2 divided by sin beta 2 minus mu cos beta 2. So, depending on the inclination of Doppler wear and coefficient of friction and reaction fiber force on fibers. So, S2 can also be calculated. So, the magnitude of the reaction forces S1 and S2 depends on the density of fiber layer. As I have mentioned, more density, higher will be the reaction force on each clothing in case of metallic wear clothing. But in case of flexible wear clothing, there are other problems comes, it is not that straightforward. In case of flexible wear clothing, the density depends upon the relative extent to which the card clothing filled with the fiber. By the ratio, the absolute magnitude of Q, that is load to the fiber embedded inside the clothing. So, in flexible clothing main problem comes the fiber gets entrapped. So, that is the these are the function on which the card clothing that load depends. So, according to Baturin, the slight approximation, with a slight approximation it can be assumed that the ratio of the reaction of fiber layer on the card clothing is equal to the ratio of the relative degree of occupation of the card clothing with fibers. Okay. And in the case of flexible card, or the ratio of the load to the metallic card. So, in case of metallic card, it is a ratio of the load. So, the with a slight approximation we can assume S2 by S1 equal to QD by, that means load on the Doppler by entrapment power of the Doppler. The entrapment power term comes when we use the flexible clothing divided by the ratio of the load and entrapment power of the cylinder. So, from the equation that we for metallic cut clothing QD and QC are negligible, because it is there is this terms are less because fiber entrapments are less. So, for metallic clad clothing we S2 by S1, it depends on the only load on card. So, this is again a constant for fiber transfer based on the wear point density, wear point inclination. So, this is again transfer efficiency based on wear point efficiency. Earlier we have seen K1 based on wear point density, here wear point based on wear point inclination. So, we can calculate K2 or QD by QC. So, K2 is the characterization of the ratio of entrapment power of the cut clothing in relation to the angle of inclination of the wear point. So, it is based on the angle of inclination. So, from expression 5, this is the expression 5, what we can get. So, S2 by S1 we can calculate again, and by rearranging this equation we get the relationship between S2 and S1. So, in actual practice the entrapment power depends not only on the inclination of the wear point B1, beta 1, beta 2, that we have discussed, and but also inclination power of the respective perpendicular plane passing through the base. So, here the alpha 1 also is passing through the base in the boundary of the interacting surface. So, it is in actual practice not only the beta 1 and beta 2 are the factor, but it is with respect to perpendicular plane, the angle at the with the perpendicular plane alpha 1 and alpha 2. So, that we are going to show in the discuss in the next slide. Okay. So, here we can see this is the angle alpha 1 for cylinder and alpha 2 for doffer. So, alpha 1 and alpha 2 are the angles with the perpendicular of the plane. So, alpha 1 and alpha 2 are the angles. So, inclination of the wear point with respect to perpendicular plane passing through the base of the boundary of the interacting zone, that is alpha 1 and alpha 2. From the diagram it is clear, and beta 1 and beta 2 as we have already discussed, and they are interacting. This is the fibers, interacting fiber. Now, this angle is also important, because here now we are trying to discuss here. So, now here alpha 1 we can calculate, alpha 1 the sin alpha is h by L3. So, that is we can from the this is h from geometrical derivation we can calculate. So, alpha 1 is equal to sin inverse h plus L by 3 by R3. So, through the derivation we can do, we are not going to go in the detail of derivation. Alpha 2 is sin inverse h minus L by 3 by R d, where h is the distance of the boundary of the zone interacting from the central line. This is the central line, and this is the distance, okay, h. R is the radius of cylinder, R c, R d is the radius of doffer, L is the fiber length, length of fiber. Okay. When the curvature of cylinder and doffer are considered, which are the characteristics angle characterized by angle alpha 1 and alpha 2. So, if you change the curvature, so alpha 1 and alpha 2 changes. So, now we are discussing the diameter of the rollers, both cylinder and doffer. So, alpha 1 alpha 2 changes, the coefficient, then the coefficient K 2 becomes Q d by Q c. So, K 2, this is the K 2. So, where we are considering the alpha 1 and alpha 2. So, that earlier it was cos beta plus mu sin beta, but here it will be cos beta cos beta 2 and mu sin beta 2. For doffer, the alpha 2 will be added, and for cylinder alpha 1 will be subtracted. But the effective angle here, if you see, this is the beta 1 and here is alpha 1. So, effective angle will be the beta 1 minus alpha 1, and on the other hand, for doffer it will be actually beta 2 plus alpha 2. So, this is the relationship. K 2 is modified here. Okay. So, now we are coming to the influence of centrifugal force. So, what we have discussed, the influence of wear point density, influence of wear point angle, and also influence of the next is influence of centrifugal force. So, here this is the angle of the wear point of cylinder beta 1, and centrifugal force is acting outer direction. Okay. So, it is trying to take out the fiber from the cylinder surface, and this is the diagram which we have already discussed here. Now, centrifugal force acting on fibers influence the load on the cylinder. When the centrifugal force is more than the retaining force of fiber, so when this force is more than the retaining force of the fiber for cylinder, that means C c is actually sin beta 1 minus mu cos beta 1 is more than the resistance force. So, this is the R here, R cos beta 1 and mu R sin beta 1. So, the fiber, the force on the fiber acts downward, but force the centrifugal force effect will act upward. Okay. So, this is actually, if it is more than the force on due to the fiber tension, then in doffer it is again, if the centrifugal force is more, so this will happen. So, C c and C d are the centrifugal forces on fiber on cylinder and doffer. So, R is the reaction force acting on fiber, that we have already discussed. So, this is the condition for centrifugal force. Pilow's actual data which shows the following relationship between the load on cylinder and doffer clothing, varying cylinder speed. So, Kw Qc by Qd, and Kw is given by that relationship from the data. This is the relationship where Rc is the diameter of cylinder and Vc is the linear velocity. Kw Kw coefficient characterizing the influence of centrifugal force. So, here centrifugal force influence is there Kw, and Vc is the cylinder surface speed. The centrifugal force comes from the cylinder rotation, and Rc is the cylinder radius. Now, we can see, so Rc if increases, so the Kw will transfer coefficient will increase. So, coefficients we have discussed 3 different coefficients K1, K2 and Kwd. Kwd, this coefficient change the slope of the line depicts in the relationship between Qc and Qd when entrapment power of both surfaces are same. So, that means it depends on the slope of the line. Okay. So, relationship between Qc and Qd, this is the relationship. So, Qc Qd, if Qc equal to Qd, then this is the straight line relationship will be there. Now, here it is Qd, if Qd is equal to K1 K2 Qc, and here in this equation it is a Qd equal to Qc, another relationship, this is the relationship here. So, at different combination we can get the transfer efficiency. So, the influence is that the relationship between the loads on cylinder and doffer becomes this, as we have discussed, this that the constant. So, if we consider the influence of the centrifugal force, the another constant K3 comes, that is transfer efficiency. So, where transfer efficiency K3 is equal K1 K2 by Kw. So, total transfer efficiency is the weight of the fiber delivered by the doffer in unit time divided by weight of the fiber presented to doffer by at the same time. So, that is the transfer efficiency. So, the amount of fiber delivered by the doffer per unit time is Qd Vd. So, Vd is the speed and Qd is the per that is the amount on the load on the doffer. So, load on the doffer per unit length. So, Vd is the speed. So, total amount will be, so Qd multiplied by Vd. So, the downstream from the zone of interaction between cylinder and doffer, the load on cylinder is, this is the load because transfer coefficient is there, and Qd is the load on doffer. So, Qc we can calculate. So, after adding the addition of the load P gram per meter from the Licarin. So, Licarin we are adding the total load of fiber, okay, layer beyond the Licarin and cylinder interaction zone. So, that means the total load in the cylinder Qc plus P, Qc, that load on cylinder and additional load. So, the amount of fiber presented to doffer per unit time by the cylinder per unit time will be this. This is the cylinder speed and load, okay, that is per meter it will be the load. So, Qc is, we have derived the Qc, so that we can get this relationship total load. So, the amount of fibers presented to doffer by cylinder when waste is neglected. So, we are not actually in this calculation, we are not taking the waste into consideration. So, delivery equal to feed at that time. So, always it is a waste, if weight is not there, whatever material is fed, that is delivered. So, QD VD equal to P multiplied VC. P is the amount of material fed always. So, the amount of fiber presented to doffer becomes this. So, this is the material on the load card and additional material. Okay, additional material is there. QD VD, this is on the doffer. So, the amount of fiber present to the doffer. So, doffer it was there, and then additional we are adding here. So, delivery equal to feed here, this is the feed and this is delivery, the amount of fiber presented to the doffer, this is the total amount of fiber we are presenting to the doffer. So, the transfer efficiency K, overall transfer efficiency, if we see, this is the overall transfer efficiency, so, taking into consideration of all the factors together. What is that? QD into VD, that is the total material actually presented, it is delivered, divided by total material presented. So, what is the, that is the material transferred to the doffer, and this is the material presented to the doffer. So, that is the overall transfer efficiency when we take into consideration of all the factors. Okay. That is the inclination, that is K1, K2, KWD and the QD, QC. So, everything is actually taken into account. So, if we rearrange this equation, this will be this where velocity of cylinder, velocity of doffer, everything is taken into account. So, from this relationship, if we take the consideration of all the factors, we take this relationship. If we try to eliminate some factors, then we can assume this as unit. So, you can simplify which parameter is important, that we can take into account. So, here is the transfer efficiency, we just replace the material factors. So, K3 is another factor is which has been taken care. So, so VD K3 by VC K3D. So, K3 is the K1 K2 by KW. So, this transfer efficiency K, it takes care of all the parameters. So, last Simpson's analysis is that the proportion of fiber transferred to doffer depends on the following ratio of the wear point angle. That is the we know that ratio of the wear point angle, that is R equal to sin beta 2 plus cos beta 1 divided by sin beta 1 by cos. So, as per the Simpson analysis, the transfer efficiency, the fiber transfer to the doffer is the proportion of the ratio. Okay. So, inclination angle of beta 1 is the inclination angle of cylinder wear point, beta 2 is the inclination angle of doffer wear point, and here we can see the maximum value of beta 1, that is cylinder, it is 90 degree. So, for synthetic fiber we try to keep it 90 degree or close to that, and beta 2, that is the Doppler angle, it is 45 degree. So, that is the maximum value, and from there we get the R max, that is the maximum the fiber transfer coefficient, it is 1.414. However, since the cylinder wear point angle 90 degree would not give good carding action. So, we need little bit carding. So, hence angle 88 degree for the cylinder and 45 degree for Doppler is suggested as a maximum angle. And as per the Simpson's rule, Simpson's analysis, this is the simplest analysis which he and this relationship came from the detailed derivation that we are not discussing, but as per Simpson's analysis we can directly get the R max value. R max is the proportion of fiber transfer. So, that we can get here, and that is the end of this session. Thank you. We will discuss the next topic in the next session. Thank you.